jointly organized by Frontiers of Computer Science, the Journal, iGroup, and Newswise. Today, we are bringing together two distinguished researchers who will share complementary perspectives on the field of artificial intelligence. Professor Gert Cowenbergs from the University of California, San Diego. He's an IEEE fellow and a pioneer in neuromorphic engineering and brain-inspired computing. Our second speaker is Professor Sijin Bian from Northwestern Polytechnical University.
Hello, everyone.
He focuses on bio-inspired sensing, neuromorphic perception, and embodied intelligence. Welcome, Professor Gert Cowenbergs, for the first presentation. Go ahead, Dr. Cowenbergs.
Thank you. So, well, I'm very excited to be here this morning or evening. So this presentation will highlight advances in neuromorphic computing memory arrays for massively parallel AI at extreme scale and efficiency. And we all know the advances that we have seen in AI, artificial intelligence, over the years, and it has been amazing, right? Here we see another order of magnitude improvement over a decade, right? And it's all fantastic. But consider that those advances in AI have come at tremendous costs in the energy consumption and the amount of computation being performed. To the extent, right? So that's just one order of magnitude improvement in the error rates have implicated about 8 or 9 orders of magnitude increase in the amount of computation, floating point operations being performed, or equivalently the power being consumed to the extent that it just to train one model of say, ImageNet, it now takes about the entire energy budget of New York City in just 1 month. So it's totally crazy and of course not sustainable in the future. So clearly, and a very important aspect of neuromorphic computing or AI in general is, can we somehow reduce the footprint, the energy footprint, and do it much more efficiently in energy? And then it's important to consider the, I call here the energy efficiency spectrum. So the horizontal axis here, depending whether you like the glass half full or half empty, operations per second per watt, right? How much bang you get for the buck, right? So the throughput versus power, or equivalently 1 over that, so the glass half empty, it's the joules per operation, right? That's right. How much energy do you have for each operation? And so clearly this is a very vast scale. And so on the limit here, Landauer's limit tells you for each bit of computation or storage, right, you require about a thermal energy. K is the Boltzmann constant, T is temperature for each bit, right? And that's roughly 10 to the minus 21 joules, right, for each operation. On the other end of the extreme is what is practically achieved still today, or maybe yesterday, right, with CPUs or DDR memory. Right? And I should mention, it really, the compute for AI is mostly limited by the memory access as opposed to the actual compute itself. So here we're talking a few picojoules per bit for each, right? For each memory access in DRAM, that amounts for say 8 bits of memory for each multiply cumulate, say for a synapse, about half a nanojoule per Mach. So clearly, orders of magnitude worse, right? And the brain is somewhere in the middle, actually closer to the Landauer limit. A femtojoule per synaptic operation, which is actually very simply arrived at. Neurons spike about 10 hertz, 10 times per second on average. We have 10 to the 15 synapses, the connections between the neurons in our brain. They're all active when a neuron gets fired, right? So that's 10 to the 16 synaptic operations per second, right? And our brain consumes about 10 watts of metabolic power, roughly speaking. So the ratio of that gives us, right, this is 10 to the 15 operations per second per watt, or 10 to the minus 15 femtojoule per synaptic operator. So clearly, this is great. And how can we get closer to that? Well, all the advances we've had over the last 10 years or 15 years have not really pushed us that much farther, whether it's FPGAs or GPUs, because still they access mostly sequential memory off chip. Fancy high-bandwidth memory is still mostly off-chip memory. And so clearly, all right, so that only gives us a factor 10 improvement. Clearly, we need to do better than that. And so the great advances have been in what's called compute in memory. Why don't you bring the compute closer to the memory, in fact, inside of the memory? And that's how you can really get great advances of massively parallel operations, where the vastly parallel memory itself, right, will also come with vastly parallel compute all tied together. I'll show some highlight how those advances of coding is actually very close to human brain's performance within a factor 10 with Mamistrov or RM-based computer memory. And I'll show even where we can beat this further by using adiabatic energy recycling techniques, where we can even recycle some of the fundamental electrostatic energy in a compute. So very exciting. So I'll dive into it. So neuromorphic engineering takes inspiration from the brain of not only compute as the brain is doing in terms of the algorithms, but also adhere to the fundamental physical principles of how neuron synapses physically are organized as architecture, and also the fundamental principles of, say, the thermodynamics of the compute, in order to achieve those physical realizations of those neural circuits in silicon that not only perform well in terms of what they compute, but also that are very energy efficient and very resilient to errors, natural errors in the implementation and the unpredictable environment in which those things operate through learning and adaptation. So that's the premise of neuromorphic computing, right? So neuromorphic stands for neuro and morphic, right? So you actually morph neural systems into silicon systems, right? And that has been the principle over the last 30, 40 years. Let me just summarize why this is important and how this advances us to great efficiency and resilience, in addition to really great neural computation. Well, for many years, neural systems have been studied by neuroscientists in an analysis framework, basically reducing everything to the least common denominator of complexity and then analyzing that in isolation. Well, engineering is the antidote or the opposite of analysis, right, of science, by synthesizing from the ground up and basically doing systems analysis at each level of scale, where you only take care of that level of scale and then just abstract anything below it. And so it happens that at each level of scale in hierarchy, right, all the way from whole brain systems down to ion channels, right, and use molecular scale of neural systems, there are isomorphisms, physical isomorphisms between, say, what is happening in the biology, biophysics, and then the physics of what is happening in silicon, whole solid state. Even though those media are vastly different, they're actually quite similar principles at play. And actually, the Boltzmann distribution is at play almost everywhere here. So we can have those Boltzmann machines, right, or those Boltzmann energy-based models of, say, how the brain computes, all the way down into how ion channels operate, where you have ions going to ion channels versus electrons or holes that go through channels of transistors. And so that allows us to build systems from the ground up that actually really emulate the physics, the biophysics, right, using silicon. And that's the premise of neuromorphic computing. Just to highlight here, right, so the same exponential distribution of conductance or currents versus membrane voltage or gate voltage of a resistor, they all play out, whether it's an ion moving through an ion channel through a membrane of a neuron or any electrical active cell, or equivalently a channel of a transistor in a modern or even ancient MOS, metal oxide semiconductor, field effect transistor technology, right? In fact, the same Boltzmann distribution is given by the energy landscape, right? The energy barrier that the gate implies for transport of ion of in this electrons, right, across a channel plays out also through those channels of biophysical elements in biology. And so this exponential distribution has been the founding principle for very efficient analog integrated circuits that operate at extreme efficiency owing to this 6 order of magnitude of dynamic range that you have a conductance for voltage and be able to really get massive gain, great efficiency. In fact, that's the best region of operation of the transistor, is the subthreshold region of operation for the MOS transistor. That's also the subthreshold region of operation where many of those cells in biology operate. And so that you can really exploit for doing very efficient computation. Here's some examples, right? Silicon retina, many years ago, by my colleague here, now at Stanford, right, where you map all the functions, the retinotopic functions, right, on the retina, silicon retina, photoconduction here with those green elements, and then all the circuits around it. You have horizontal cells, bipolar cells, American cells, and then the ganglion cells. Those are the cells that actually spike and then convey the information to the rest of the brain through the optic nerve, right? So sure enough, you can build the circuits that emulate spikes, the spiking of the optic nerve and going to the rest of the brain that capture spatio-temporal information very succinctly on the focal plane. And so doing processing on the focal plane allows to do very efficient processing, just like how the human brain is doing it. In fact, very efficient processing on the focal plane is a hallmark, right, for focal plane compression, the same kind of compression that is now emulated, say, with MPEG, right, but much more efficiently in a spike-based fashion, just with a few transistors on the focal plane. Here's an example, an actually engineering example, how we have further leveraged that. Exchange threshold detection, CMOS imager, right? So we're just adding a few more pixels in addition to the standard APS active pixel sensor that you have in a CMOS imager will give you this, will efficiently encode this temporal difference of information on the focal plane. You can see here clearly on or off events slightly increase or slightly decrease in intensity locally, right? And that's enough for you to know what's going on in the visual scene. This principle of dynamic vision sensors has been highlighted in modern vision sensors as opposed to just cameras, as AI front ends, right, for vision systems, whether it's vision transformers or others like today, and allow this very efficient compression for applications, say for surveillance, etc. Right. So this, and what is in common between all the systems here, the sensor systems, is that they very efficiently encode the sensor world into events. In this case, those events are temporal events or spatial events, right, that encode what is happening in the scene. And those events are then spikes or action potentials, right? So neurons fire action potentials that propagate, right, from one neuron to the other neuron in the network through synapses, right? And so the neuromorphic engineering community has built those systems not only for doing the sensing, silicon cochlea, silicon retinas, silicon olfaction, etc., right? But in addition, has built those processors that are event-driven, that act on spikes, and that even act based on implementing this added event representation. This basically having lookup table to define when a neuron fires, where does it go in the network in a virtually wired as opposed to physically wired system, where basically memory encodes the connection strength or the connection topologies of the network, right, very efficiently. And those are very reconfigurable because you can just change entries in the table that defines how a neuron connects to another neuron by basically changing entries in the table, right? So you can basically have plastic systems. Plasticity means the ability of the brain to adapt itself over time through activity by basically just rerouting connections by changing entries in the tables. Right? So that's the principle of reconfigurable synaptic connectivity and plasticity that is being exploited for building very efficient systems with virtual connections, basically implementing the brain at large, almost any connectivity, but basically reconfiguring the connectivity, right, in those systems. Just to highlight a few where we're going here. So Scale is extremely important, right? We're dealing here with brains that have 10 to 15 synapses, right? And so clearly, we need to get to systems that can equate that level of complexity of 10 to 15 synaptic operations per second, 15 watts of power, right? So, and scaling is actually important, and actually it turns out in our advantage, right? If you look at, say, machine complexity, what you pay versus task complexity, what you get. So, right, there's a thing, there's the buck for the bang, right? On a log scale, right? So digital systems, AI, classical old school AI has had this curse of dimensionality, right? So in which harder problems have become even more tremendously harder for the machine, right? And then scale poorly, worse than linearly, right? And that's why we have for many years had the curse of dimensionality. It was getting more difficult once you get really hard, interesting problems, right? Whereas for analogic rather than logical computation, where you do approximate, massively parallel pattern-based processing that is analog and massively parallel as opposed to just purely digital and sequential, you get, rather than the curse of dimensionality, you get actually, I would say, the blessing of hyperdimensionality. The higher dimensions you go, the better it gets to the central limit or anything that, right, basic statistical principles. So you can get better performance, right? Better approximate reasoning, the more complex things get. And so that is the premise of neuromorphic computing, or this analog-based style of computation, right? And so that have been pushed forward with the modern AI, this I would say neuromorphic AI that uses deep learning to abstract lower dimensional representation of the world, and then neuromorphic engineering that gets us at this really large-scale systems, right? About two principles. If you want to minimize energy per task, it's simply decomposed into, you minimize energy per operation and operations per task. And so those two just beautifully partition into energy per operation is minimized by just building this compute and memory architectures that do more for less, right? So that basically just a femtojoule of operation per synaptic operation versus the tens of or hundreds of picojoules per multiply cumulate in typical digital accelerators, right? And operation per task is also minimized by this deep learning, basically having better approaches for doing learning. So those two need to come together, those advancing the technology, right, for neuromorphic compute, as well as also advancing the algorithms and the models, right, for handling the complexity, right? And I'll just briefly highlight those two complementary perspectives of how deep learning, which is the green, and the neuromorphic compute, which is the blue here, work together, right? And so it just so happens that multiple disciplines all come together for doing so, right? Whether it's, I mean, for getting systems that can scale to 10 to 15 synapses, right, at just 15 watts of power. You want to get truly great efficiency in massively parallel systems and 3D integration of memory on top of silicon that can really get you those densities, right? And then so we also want to route things in a hierarchical fashion for actually scaling this, right? On the complementary side of neuroscience, computer science, cognitive science, right, we have to then handle complexity in a very efficient manner as well. So here's some a snapshot of, I wouldn't say it's the latest, but actually still pretty much the state of the art in large scale reconfigurable neuromorphic computing. Those are systems that are event driven, handle spikes, events, and that can be wired dynamically, as I mentioned, right, with this event-based representation. And so you see here that we have many systems where it's digital or analog. You recognize Spinnaker, Spinnaker 2, Louis is Intel, Louis 3 is now out. True North, there's now North Pole from IBM. And then there are all the analog systems, right? The Facets, Brainscale, Heidelberg systems, Stanford Neurogrid, our own work of the integrated 5-array transceivers, IFAT, UCSD, at INI Zurich, there is the ROLL systems, right? And they all are advancing over digital accelerators. And the key here is that energy efficiency, semantic operations per second versus watts, or conversely, as I mentioned, joules per semantic events. So it's typically in the order of a few tens of picojoules per semantic operation. Is that good? Well, that's already a lot better than closer to what the brain is doing, but still far away. And I'll highlight how we can actually do even better than that, right? And so there are two aspects of doing better. First of all, you need a scale, and scaling is not just a matter of building large-scale, massively parallel systems, but also you want to make sure that messages can actually come across. This is Amdahl's law actually addressed by the white matter and the gray matter of the brain, right? So sure, we want to be able to connect very densely, and that's the flexibility of the gray matter, right? A synapse is very densely connected with arbitrary connectivity, but you also need to be expandable. You want to make sure that each neuron, in principle, many neurons in the brain connect very far away, not many, but quite a few connect over long distances. You have this small world model, right, where everyone is in the world is connected about six steps away from anyone else, right? So same is true in the brain. So you have this hierarchical, this structured hierarchical topologies in the brain that are tree-based, right, structured that allow you to hop in just a few logarithmic steps, right, to the brain for reaching almost any neuron, right? And so you need to have both this tree-based topology as well as this arbitrary connectivity, and that's what this hierarchical additive event routing does, right? So we have the white matter efficiently implemented, this long-range connectivity, very richly implemented through this hierarchical additive event routing schemes, and then you have this local flexibility implemented, right, with this dense crossbar arrays of synapses. Right? And so here it is shown how it works. We have those systems implemented in silicon that implement neurons, and then we have synapses implemented in memory around it that implement this reconfigurable connectivity. But this is done in a hierarchical fashion, right? So when on this chip, when neurons fire, they fire exponentials, they go out, and then externally we have this memory access, right, through this FPGAs here that could go to these memory tables in memory that define where that event reaches other neurons in the network, and those events are then again transmitted, going into the chip, and then there is that is encoded and then transmitted to other neurons in the network, right? So we have this arrays of neurons that are addressable, and we have this input events and output events, synaptic input events that define inputs of the neurons, and then neural output events that define where once the neurons spike, where they go, right? It's important to note internally, everything is analog. Those neurons are analog, but externally we have digital an interface where you have spikes in and spikes out that are asynchronous digital events, right? And this is a hallmark of neuromorphic compute, where it can do very efficient communication in digital, while internally you have very efficient compute in analog. Right? It's all great, except this consumes, again, as said, tens of picojoules of energy, because you mostly go outside for accessing memory. And that's the key here. So how do you do better than that? Sure, we bring the compute closer to the memory. In fact, as it happens, modern memory today, whether it's phase change memory or RAM, which stands for resistive random access memory, or M, right, so magnetic MRAM, magnetic RAM, those are conductance-based memory technologies that are non-volatile and extremely efficient and dense, that are now leading advances in memory technologies today. As it so happens, a conductance-based connection is also a synapse. So for every bit in this conductance-based memories that you have now, this right, whereas PC RAM or RRAM, you can actually recycle and reuse this same element rather than just one bit in a memory that is just serially accessed as a synapse in a neuromorphic network, where the word line is basically your exponential, presynaptic exponential that drives this conductance here, this right, and the bit line, that's your dendrite that accumulates information, right, from all the synapses. So you can just accumulate, and then basically, voila, there you have a biophysical synapse. So each memory element, each bit of a memory in a digital modern memory is actually dubbed as a full biophysical synapse in a massively parallel network. And that's exciting because now you can build networks, crossbar arrays of those synapses that can be massively parallel, right? So you have massively parallel events coming in along, say, horizontal lines, and then along the vertical lines, there you get your dendrites that accumulate, right? Information. So it's each junction, you have this conductance that is activated, right? And so physically, I can implement these 3D structures where you can implement synapses, right, in a very efficient manner, right, where you have massively parallel operations. For a matrix now of n inputs and n outputs, you have n squared operations all done in parallel in zero time, in zero order time, as opposed to typically in a digital compute, you need to go through several for loops here, right? You can even do learning. You can adapt synapses locally based on this biophysical learning rules, such as spike timing dependent plasticity, SDP, right? For doing learning that is biologically motivated. Basically, only learn when the presynaptic action potential arrives before the postsynaptic action potential. And otherwise, you depress the synapse, right? And it's kind of it's logical from a causal point of view. And so we build systems, right, that can scale, where we have those crossbar arrays of synapses directly, right, locally implemented on top of arrays of those neurons, those innovative fire array transceivers, as I mentioned. And now that can be one core in architecture. And now you have this hierarchical address event routing scheme that allow you that send messages across the network of cores in a reconfigurable manner, right, where these routers can be reprogrammed for implementing almost any connectivity. So this allows us to build large-scale systems that have this long-range connectivity while locally have this very dense gray matter connectivity. So wide and gray matter going together in a very efficient manner. So here's an example of how we implemented those systems. NeuRAM is the first seamless integrated RM computer memory chip that combines 3 hallmarks of where we want to go with this AI accelerators: high versatility in diverse architectures, record efficiency, and high inference accuracy comparable to software, right? Normally, you would think to build a very efficient hardware is going to be very dedicated to one application. No longer. You can actually have reconfigurable, right, fully programmable, adaptable architectures that can do almost anything as a microprocessor or a GPU, but now with much greater efficiency owing to this computer memory architecture that are implemented. And so, yeah, you can get now down to 1300 joule per operation, which is now a factor 10 or less than factor 100 from the efficiency of the brain, owing to this architectures that are actually only transposable, in which you can change the directions of your connectivity by locally switching activity of the neuron between rows and columns architecture. You can actually transpose the connectivity, which means you can backpropagate. You can go back from outputs to inputs in your network, which is extremely important for learning, but also for some other applications. I'll just skip the circuits, but we have very efficient circuits for implementing those crossbar arrays and the neurons that implement these connections, this reroutable, transposable architectures. And so this transposing of the direction of the flow, right, from inputs to outputs, back from outputs to inputs, is extremely important, not only for learning, but also actually for generative AI, which is now the hallmark of modern AI, right, where you can just flip the direction of basically rather going from your visible units to the hidden units. You can go back from hidden units to your visible units in your network, and this allows you to generate, to dream, right, to come up with new representations of in the pixel space, in pixel space that basically can fill in the blanks, or basically can dream or diffuse, information that is missing. And that's the hallmark. Generative AI is, of course, the modern foundation of AI, whether it's stable diffusion or modern transformer architectures, right? They're all based on this principle. So you can build this very efficient hardware. Just highlighting here, so for instance, not only can you discriminate and detect, say, this 6, but you can also then, so when you corrupt the image, you can actually reconstruct it, right? And so this reconstruction capability is, as I mentioned, the hallmark of generative AI. You can fit distributions in space as opposed to just discriminate. And this allows you to do really great Bayesian inference and do all the great stuff that we're seeing now happening in AI. And so we will do all this. It's all mapped through this very efficient layered architectures where we have this. We can map almost any architecture where it's a deep layered neural network, or it's a LSTM, right, long short-term memory, or a Boltzmann machine, or generative AI, or autoencoder. Those are all mapped by this mapping architectures onto this tiled array of this hierarchical event routing tiled array of cores in this architecture for doing almost any architecture. And then we got around the imprecision, the analog imprecision of those networks by basically doing careful modeling of the hardware, but very fundamentally, we're able to actually, through the learning process, chip-in-the-loop learning, we're able to fine-tune the performance and recover the imprecision of the analog hardware purely by learning one layer at a time and then programming it just one layer at a time. Basically, each time, then each new layer, by retraining the network, we're able to recover the imprecision that was in previous layers, owing to the massive parallel distributed representation in the architecture, where it can still take advantage of the large dimensions you have of your architecture to overcome the imprecision of its own environment. I just highlighted, I'll just wrap up mostly here, but so in addition to this resistive random access memory technologies, so whether it's conductance-based synapses, whether it's RAM or PCRAM, right, these conductance-based memories, we also have memories now that can be just purely charge-based. And the nice thing about charge as opposed or capacitance as opposed to current, right, or conductances, is that you can actually really recover the energy that it takes for doing the compute, owing to this adiabatic energy principles, right? Because a capacitor by itself doesn't consume energy. Resistance, conductances consume energy, but not capacitances, right? And so even further, we can get rid of noise because you can actually avoid KT-VC sample noise in the process of doing this compute. The principle is actually quite simple, right? You have this crossbar arrays of now charged elements, charge coupled elements, or charge injection device elements, just like in a DRAM where you store charge, but rather you store the charge, actually use a charge in the computation process where you can selectively move the charge from your input line to your output line, capacitively coupled, purely, right, in this process, right? So this is a non-destructive process. You just move the charge and get it back after, right, when you bring the voltage back down. This transfer of charge not only is charge conserving, but is even energy conserving if you do it carefully, if you drive the lines very carefully. In fact, it's a very simple principle. Most CMOS circuits consume dynamic power due to the fact that the charge that is needed for charging a capacitor, the output, right, comes from one supply and is returned to the other supply, two static supplies. So you lose entire voltage, entire potential in the process of one cycle in your compute. If you use a hot clock rather than having DC supplies, but have a hot clock where you basically alternate the voltage, right, on this hot clock line, you can actually recycle the energy, but because rather than returning it to different supplies, you actually adiabatically drive your lines, right, with zero voltage across the switch here that is driving this outputs. And this is a principle of energy recovery logic that has been used for many years. It's called adiabatic digital compute, and there's now we're been researching this now for analog compute operations, where basically we have this array of charge-based elements that are now driven with this ERL drivers, coupled with an external inductive tank, and then this, right, so inductor. And so this tank of this inductor and this capacitive array here of synapses is at resonance At resonance, we recycle, right? Basically, we go back between electrostatic and magnetic energy and recycle almost all the energy. Almost 99% of the energy is recycled, or 98% is recovered, which means we're operating here at less than a femtojoule of energy per multiplied cumulative. In fact, our latest work show we can actually go down to 10 to 100 attojoules per multiplied cumulative. That's a world record. We're able now to compute, right, at a fraction of the energy that any digital or even analog system can do today. Very exciting. And even for communication, we can use the same principle by recycling the energy that this takes, right, for sending a bit over wireless link by us, again, closing a switch only when the voltage crosses zero. Very simple principle. And so this way we can actually send data wirelessly at just less than around a femtojoule of operation of bit, right, being communicated wirelessly. So that's also very exciting. So just the many exciting things. I haven't said much about the actual algorithms, but I'll leave that to some other experts in the field. But yeah, AI is really great today. You can do deep learning, and important thing to note here is we can even have learning algorithms that exploit the natural stochastic nature of those synapses, right? And so this way, you can actually do compute in a statistical fashion that is actually extremely efficient. We have put all the resources available to the community. You can go online and have this compute in memory architectures with FPGAs implemented. Implement your Python code for doing deep learning on this system with 40 billion synapses, 160 million neurons over the neuroscience gateway. We call this the higher spike system. Anyone is more than welcome to use it. And I'll stop there. Sorry, I probably went over time.
Okay, thank you, Dr. Cowenbergs.
I should mention that I'll share this, but all the references are also included here. I'm happy to share those slides with everyone. Yeah.
Okay, great, thank you. We'll invite now Dr. Beyond to present about his work.
Yeah, just wait a moment. Let me share the screen. So, can you see the screen?
Yes, we can. Thank you.
Okay, great. Thank you, everyone, and I'm actually very happy to share some thoughts after years of work in the neuromorphic field. So the title is, for me, is Neuromorphic Sensing for Embodied Intelligence. And this title is recommended by the organizing committee, and I like it a lot because it matches my work very, very well. So the central idea of this talk is simple. So if you want the machines to behave intelligently in the physical world, and we can not only build a better artificial brain, we also have to build a better sensory system. So that is my claim. So my work started from embedded neuromorphic hardware, especially the Kanken system and some applications platforms built on top of it. But over time, the question shifted. So I became less interested in asking only how efficiently we can compute, and more interested in asking what form of information should enter the computing system in the first place. So let's start with this ghost knife fish. So while most fish rely on the sight or smell, knifefish use electrolocation, so they continuously generate a weak pulsing electric field around their bodies and use the receptors on the skin to detect the disruptions caused by the nearby objects. And because of this unique ability, knifefish actually displays several specialized smart behaviors. First, the instant spatial awareness. So they can pinpoint the exact distance, size, and even the material of objects in the murky waters. And second, the omnidirectional movement. So Their unique ribble-like face allows them to move forward, backward, and also hover with incredible agility. And third is the complex social communications. So they use those electric chirps to communicate with mates and avoid jamming each other's electric signal. So there's a simple question: why is a knife fish intelligent? Is it because it has better brain, or because it senses the world differently? So the common intuition that intelligent behavior comes from the powerful brain. That is partly true, right? But it is incomplete. The brain does not receive wrong pixels, wrong pressure waves, or the wrong chemical concentrations. So before the signals arrive in the central nervous system, peripheral structures actually have already imposed structure on the world. And they're not generic analog to digital converters. So they use front-end computational organs, and they decide what is silent and what can be ignored. This is a biological inspiration behind this talk. So first, the intelligence never begins with the brain. It begins actually with sensing. And second, the brain does not receive the wrong data, and it receives already structured events. So this slide shows the arc of this talk, right? I will begin with Kanken and some Kanken-based embedded edge systems because they were my entry point into the neuromorphic engineering at ETH. So those projects looked like hardware projects, but for me, they created a system-level question. So what does it mean to build an efficient perception to action pipeline? Then I will move to event cameras and low-power eye tracking project, where the sensor itself already performs an event-based transformation. From there, I will generalize the question beyond vision. So if a dynamic vision sensor can be beyond inspired, why not the other sensing front end? So I will argue that encoding is not a pre-processing step. It is first layer of intelligence. And finally, I will close with a broader vision. So beyond inspired sensing as underestimating front end for embodied neuromorphic intelligence. And here are some images of my journey of the neuromorphic field. So Kanken was designed around a hybrid idea. So on one side, there is event-based perception and spiky neural edging. And on the other side, there's frame-based perception and conventional neural network accelerator. So instead of assuming that one paradigm replaces the other, the system asks how both can coexist in a low-power embedded platform. So this matters because embodied systems are messy, actually, right? A variable system may need fast event-based reaction, but it also may need richer frame-based context. So Kanken was not only a chip, it was question about the whole loop. So we built the Colibri UAV. This is a platform by integrating the event and frame interfaces and also the processing the accelerators into a complete embedded system. So the scientific lesson for me from this project was not that neuromorphic engineering cannot stop at the neural model of the accelerator block. The event sensor interface and the data movement path and also the representation are some part of the architecture. So once you see the full path, sensing is no longer outside the computing problem. So it becomes the first architectural decision. And here are some hard numbers about the Colibri UAV. So I will just skip this end-to-end evaluation. And after those projects, I started to reinterpret what I had been building. So the more I looked at complete systems, the more I realized that the first bottleneck is often the information stream, like what is being sensed and what is being transmitted. Does the representation match the physical dynamics of the task? Those questions came before the model architecture, and they also determine whether the energy efficiency of neuromorphic processor can actually be realized. So if the processor produces the wrong representation, the processor is forced to spend energy recovering structure that could have been created at the front end. So event camera reports local brightness changes synchronously. That means that the sensor itself has already made a decision about what deserves representation. So this is why event camera are so central to neuromorphic sensing. So they show that a sensor can embody an algorithm. It can transform the physical world into a temporarily precise event stream before the processor sees the data. For neuromorphic engineering, this is powerful because it aligns the sensor output with spiking computation. And the sensor and the processor speak a more similar language, which can reduce latency and energy while preserving the temporal structure of the physical world. And the retinal eye tracking project is a concrete example of this idea. So it used event camera mounted on glass and a spiking neural network regression model deployed a low-power neuromorphic processor. The result was an end-to-end pipeline with power around, if I remember, just 5 milliwatts and latency around 6 milliseconds. So the important part is that the whole chain is neuromorphic, is split. Like the sensor is event-based and the model is spiking. Also, the processor is designed for ultra-low power event processing. So this makes the system more than a compressed neural network, right? It is sensing computation pipeline where the representation is already adapted to the dynamics of the task. So this brings me to one of the most important sentences of this talk. Every sensor deserves its own neuromorphic representation. Event cameras are the most mature example because dynamic visual sensors have a clear biological analogy. But embodied systems do not live on vision, live by vision alone. So for each modality, we should also ask what's the equivalent of a meaningful event might be. Like, is it a change, maybe a threshold crossing, a temporal pattern, a frequency component, or a special contrast? So the answer will not be identical across sensors. That is exactly the point. The neuromorphic sensor is not a universal format, right? It is a design of modality-specific representations for efficient embodied behavior. So once we generalize beyond event cameras, we arrive at encoding. For dynamic vision sensor, part of the encoding is built into the pixel circuit. But for many other ubiquitous sensors, we need to decide how to convert those signals into spikes or events. This may sound like a technical pre-processing, but it is much deeper than that. Encoding decides what information is preserved and what is compressed, what time precision is kept, and finally, what the downstream spiking neural network can learn. So it also determines the firing rate and therefore the energy cost of the neuromorphic processor. In other words, encoding is a scientific problem. It links the physics of the sensor to the dynamics of the neural model and finally and also to the constraints of the hardware. Here, I want to make a claim that encoding is not pre-processing. It is the first layer of intelligence. In many machine learning pipelines, pre-processing is considered as a necessary step, but uninteresting step. But in neuromorphic system, the encoding is part of the computation. It determines the spike timing, spike density, temporal precision, robustness to noise, and also the information loss. So actually, the biological sensory systems shows this very clearly, and they do not passively digitalize the vote. They convert the physical stimuli into the neural codes that are already adapted to behavior. So if we want to build efficient embodied systems, we need to take encoding as seriously as we take the model architecture. So a useful way to think about encoding is to look across the biological modalities, right? The retainer emphasizes spatial and temporal contrast. The cochlea performs a mechanical frequency decomposition before the auditory signals reach the higher processing centers. And the vestibular system encodes acceleration and orientation in ways that are useful for balance and action. So those systems do not use one universal representation. Their codes are shaped by the physics of the stimulus and the behavioral needs of the organism. So this is a biological argument for sensor-specific neuromorphic encoding. Instead of forcing every signal into the same sample data format, we should ask what neural code makes sense for that modality and task. So to study the coding, we used the inertial sensing as a case study. So unlike the event camera, the IMU sensor does not naturally output spikes. So the question becomes how should this signal be represented for a spiking neural network? Should we encode the values as the spike rates? Should we encode the timing with time to first spike? And should we emit spikes only when the signal changes? So each choice creates a different information stream. It changes the firing rate, the temporal structure, and the robustness to noise, and also the cost of deployment, actually. So this makes IMU-based activity recognition an ideal lens for understanding encoding as a design problem. So the four encoding schemes that we evaluated can be understood as four different beliefs about time. So rate encoding says that information is represented by spike frequency over a window, and it is often accurate, but it can require many spikes. Time to first spike encoding says that information is represented by when the first spike occurs, and this can be very sparse and low latency, but it may also be sensitive to spike errors. And binary encoding maps values into binary channels and creating a structured, discrete representation. And auto modulation says that spikes should occur when the signal changes, making it closer in spirit to the event-based sensing. Those are not just technical variants. They create different meaning for spike. So the spiking neural network receives a different vote depending on the encoding. And on the neuromorphic hardware, spike density and timing are the workload. And more spikes generally mean more events to the routine and more neural updates and more energy. So the encoding scheme therefore determines whether the hardware can express its advantage. So a highly accurate encoding that produces too many spikes may erase the benefits of event-driven computing. A very sparse encoding may be efficient, but also may be too fragile. A practical design rule from this work is to begin by asking what spike should mean. So if a spike is evidence accumulated over time, rate encoding may be natural, right? If a spike should communicate values as quickly as possible, so the time to first spike may be appropriate. So this question is more fundamental than choosing the right spiking neural network architecture. It links the sensor physics to the downstream computation. And this leads to the idea of peripheral intelligence. So in a conventional pipeline, the sensor measures and the processor computes, and finally the model decides. But in a bio-inspired pipeline, computation can be distributed across materials, circuits, encoders, and neuromorphic processors. So a material may respond selectively to physical stimulus. A encoder may preserve timing and suppress redundancy. And a processor may integrate events into decisions. So this distribution is necessary for systems that must be fast and energy efficient. So if we push all those intelligence into the central model, we actually pay for the data movement and redundant computation. So at a system level, this means that neuromorphic engineering should be understood as sensor to action nervous system design. The sensor, the encoder, the processor, the memory, the communication path, and the actuator should share a timing model. So if a sensor produces asynchronous events, but the rest of system batches them into a large window, and so the temporal advantages may be lost, right? If the processor is and
I think we lost Professor Bien. Professor Cowan-Burst, can you hear Professor Bien?
No, I cannot.
I can hear you.
We lost your audio for a moment, Professor Bien, but please go ahead and continue. We're hearing you again now.
Hello, can you hear me?
Yes, perfect.
Now you can hear me, right? Am I right?
Yes, yes.
Okay, great. Yeah. So for artificial embodied systems, we need similar disciplines. So represent only what matters and preserve timing where it matters and the loop with minimal waste. And in the context of this workshop, so Professor Kalvenberg has presented fundamental contribution to the neuromorphic circuits. And my talk is complementary. So rather than focusing on how to build the artificial nervous system in silicon, I'm asking what information should feed that nervous system. So a better brain-like processor needs a better body-like sensor. So to make the message concrete, I would summarize the agenda in five principles. So first, start from the physical stimulus and the behavior, not from the model. And second, design the representation before optimizing the neural network. Third, evaluate the full loop, including the sensor readout, encoding, inference, and angle latency. Fourth, treat robustness as a property of the sensory code, not only of the classifier. So fifth, distribute intelligence into the front end when energy and latency matter. So those principles are simple, but they change how we build systems. They encourage us to ask whether a sensor should sample densely, emit events, adapt thresholds, encode timing, or exploit material properties. So let me now connect this talk to the research program I'm beginning next. So if we take the idea of bio-inspired sensing seriously, then a encoder should not be a fixed block placed before a neural network. So in most artificial systems, however, this is exactly what happens now. So we choose the coding rules and set threshold, fix a time window, then train the network, and then hope the same representation remains good in every situation. But biology doesn't work like this. The neural coding is modulated by task and attention. So the same sensory pathway can become more sensitive, more selective, or more sparse depending on what the organism needs to do. So this creates a concrete scientific gap. In low dynamic C, a fixed encoder may generate two field events and look useful information. In high dynamic C, the encoder may generate an event flood, causing the computational load and energy to rise sharply. The problem is not simply which encoder is best. The deeper question is whether encoding can become a controllable system variable. And now let me return to the sentence from the beginning. So for decades, we have invested tremendous effort in building better artificial brain. That effort is valuable and it will continue. But in biology, intelligence never begins with the brain alone. It begins with sensing. It begins with the body meeting the environment and transforming the physical interaction into meaningful neural events. So if we want artificial agents that are fast, efficient, robust, and embodied, then smarter algorithms are not enough. We need sensing, we need sensors that do not merely capture data but shape the information. And we need encoders that do not merely convert formats but increase useful neural representation. So thank you very much for the attention, and I would be very happy to discuss any part of this talk.
Thank you, Dr. Bian. Eric, too, will now moderate the Q&A portion with our professors to talk
Sure.
further about the research. Eric?
Thank you, Professor Bian and Professor Calvin-Brooks, for the insightful presentations. Now let's quickly just move into our discussion session, focusing still on this topic. I would like to start with a question for Professor Calvin-Brooks. So many AI systems today are becoming increasingly powerful, but also increasingly energy intensive. So from your perspective, how can neuromorphic computing fundamentally change the future of AI?
Excellent question. Of course, this is the core, one of the core questions, right? So how can we curb the amazing appetite of AI systems? And I wouldn't really distinguish AI and neuromorphic. I think they're all in the same family. And I think that's why I think the future of AI has to be neuromorphic. It has to address this extreme energy efficiency. And so I gave a very simple metric, energy per synaptic operation, right? You can call that just energy per Mach, whatever it is. But, and that's a key in this computer memory systems, right? Where you can really push that efficiency from a technology point of view. Of course, there's also the complement, as I mentioned, right? Having more efficient algorithms. But I think if history is an indication, typically when technology advances, when you get more for less, of course, you want to get more, right? So chances are that what we end up having is that as we get, say, 1,000-factor improvement in efficiency, rather than bringing the energy down by a factor of 1,000, most likely what we have is 1,000 more times more compute for the same energy, right? So we have to, I guess it's more, we have to exercise discipline in the usage of our energy resources, but we as scientists and engineers will just keep advancing and lower the energy footprint. We definitely can do so, and we should do so.
Yeah. Thank you, Professor Calvin-Brooks. My next question is for Professor Bian. So your presentation emphasized that intelligence does not begin only with computation, but also with sensing, right? Embodied intelligence requires continuous interaction with dynamic environments. So what role do event-driven sensing and spike neural networks play in enabling real-world intelligence?
So I would say that they play two very different but deeply connected roles. So actually, event-driven sensing changes what the system receives from the world, right? And instead of sampling everything at a fixed rate, it reacts only when something meaningful changes. So this is much closer to how biological sensory systems work. Our eyes, our skin, and nervous system, they are not passive cameras frame by frame. They are constantly selecting and filtering the information. And for the spiking neural network, it provides a natural computational model for processing this kind of sparse event-based information, right? They allow the computation to happen when the event arrives, rather than at every clock cycle. So this is important for embodied intelligence. It must perceive, decide, and act continuously, and often under strict constraints of power, latency, and robustness. So for me, the key point is like this. So event-driven sensing and spiking neural networks, they're not only tools for saving energy, they change the structure of perception itself, right? they allow the intelligence to become more tightly coupled to the dynamics of the environment of the body, let's say. Yeah, that's my opinion for this question. Yeah.
Thank you. Thank you, Professor Bian. Now, I would like to invite both speakers to discuss on more broader questions. So, Professor Bian, I'll just let you lead the following talks with Professor Cowan-Burks, if that's fine with you.
Yeah. Sorry, I ask you a second question from me. Or?
Yeah, I think next session will be you leading the discussion with Professor Cowan-Burks on
Okay.
the topics. Yeah, but if you want me to also bring some questions, I can do as well. Yeah.
Maybe I can make this question to Professor Cowan-Burks. So the current large AI models excel at reasoning, right? And but the neuromorphic system only emphasize the efficiency at real-time adaptation. So do you see that those two paradigms and as competing approaches or some other rules between them?
Yeah, no, this is of course a key point that you're raising here, Sichuan, that you already mentioned before, right? So that we are embodied, our systems, right? Our brains are not isolated. We live in a world, right? And so the interface between sensing and compute and action is extremely important. And of course, their reasoning is important because you need to make important decisions to guide your. I mean, after all, we have to survive and thrive. So I don't think it's any competition, and so it has been a myth that neuromorphic computing has been purely about lower the energy or doing things with just spikes or modeling how the brain works. It's a lot bigger than that. I would say at the time when AI became big, which was about 10 years ago, that was a time, this was not the resurgence of AI. What it really was is the resurgence of neuromorphic and neural approaches. It was in fact neuroscience that started it all, right? AI in old school, the old school AI was about symbolic reasoning, purely that, right? And nothing else. And so then what came into the mind literally is understanding of say how our brains operate. And of course, reasoning is important, but the reasoning is very different from the reasoning that you have in this symbolic reasoning. Reasoning also involves this perceptual capabilities, right? For instance, how do you play the game of Go? So everything is it, right? So you have to really look at the board and understand the gameplay, the strategies. You have to, right? And so this perceptual reasoning has been augmenting this symbolic reasoning, and I think this is really what made it go. Literally, what made it go. And I think we're getting more of this convergence. I would say today's AI is at least as much neuromorphic and neuroscience than this AI, and we should definitely, the synthesis between the two is becoming extremely important, and I think that's why we're making such great progress. It's not by chance that the founders of DeepMind, they're actually neuroscientists, and they fully understood the layer representations in cortex, the reinforcement learning. What is reinforcement learning? It's really about understanding the basal ganglia, the reward conditioning in basal ganglia, right? So brain science has really been driven, the latest advances in AI, by combining the different perspectives that are extremely important. So yes, absolutely, those things come together, and we have to keep going in that joint interaction.
I would also like to share some thoughts from my side. So I actually worked on many neuromorphic processors like the Loe 1 and 2, and also some neuromorphic edge processors from Luca Pedini's group. I joined the development, and also some neuromorphic edge processors from some startups in Zurich. so my theory is that like the spiking neural network at the algorithm side, actually it works. The progress is very good, right. Even there's a Spike GPT, right, from the group of I forgot the name of the university, but America.
Jason, right?
Very
Jason's right
yeah,
now.
very impressive. But the problem is that to present the power of neuromorphic, you really need a very good the processor, right? And my experience when developing those general neuromorphic platforms or those age specialized neuromorphic processors is really hard actually. And this is first problem, and the second problem is that I think we for this community we really need to find a very good application, a very good like the eye tracking project is very good one, a super good one, and that we use a very small event camera, DVS camera, and the H neuromorphic processor, and really achieves the SOTA, the pupil location latency and accuracy. So this we really need some very good applications. And so let's go back to those questions. I think that those two paradigms, the current AI models and neuromorphic, those projects, they're not competing with each other. I think that they're playing a complementary roles in just in different places.
Absolutely, yeah.
Great. Maybe any questions from the audience, or some questions that Professor.
Thank you, Dr. Bian. We do have a question from the audience. Hang on just one second while I pull that up here. If you have any other questions, audience, please feel free to chat those here in the Zoom chat. From Tam Lee, she asks, you mentioned the issue of an event flood in high dynamic scenes. How do you envision the feedback mechanism from the processor back to the front-end encoder operating in real time to dynamically adjust thresholds without losing salient information?
Well, the question for you,
yeah.
Zhiqian, yes, yeah.
So this is an ongoing project. This is an ongoing project. I'm still trying to. So the background of this project is that I read a lot of papers. Those papers were written many years before about those biology, those perception of human neurons. Actually, those the how our neurons, the neural perceptive neurons, like the ski neurons, they actually encode the physical signals in different ways. Sometimes they use rate encoding, right? And sometimes it will be changed to like the other form of encoding. So the spike trace generated from the ski neurons, they're not fixed. The encoding method are not fixed. And so I'm thinking how do we simulate this mechanism in math in a mathematical way, and try to build like adaptive encoding approach, and and also following this adaptive encoding, we also need to build like the encoding resistive spiking neural network. So this spiking neural network need to be able to deal with different encoding approaches. The answer to this question is that actually I don't know. I'm still trying to link the spiking, the adaptive spiking neural network and the adaptive encoding. How to link these two sides? I'm still trying to figure it out. So this is a very good question. Thank you.
Add from my perspective. So there are those hybrid systems today, right? For instance, I mentioned dynamic vision sensors. There are hybrids between dynamic vision sensors and this standard APS or active pixel sensors, right? Where you can choose, right? And so, of course, if there's a burst of events, if everything changes, let's say you have an entirely new scene, right? Of course, then it makes sense to have a frame, right? And rather than just keep sending events. Event processing is only efficient when you get sparse events, right? And so when you get a little burst, it may actually be good to combine this gets more frame-based as opposed to just event-driven representation. But yeah, those are kind of simple approaches that can, again, combining AI and neuromorphic in ways that can benefit both is a key for making advances in many of this.
And also, I remember that there's a paper, a Nature paper, like Nature communication paper, just published last year, 2025. So that paper built a encoding mechanism that has two encoding approach. Like I think it was rate encoding at time to first spike. So they can choose that neuromorphic processor can choose these two kinds of encoding, but actually still that is not adaptive. So during the real time spike encoding, the encoding is still fixed. Only before the data processing or the spike processing, you can choose the encoding. But it's still good to see that this direction has some progress. Yeah, and I believe there will be some more interesting work in following years. Yeah.
Okay, thank you, Dr. Bian and Dr. Cowenbergs. Just to draw our presentation here to a close, pardon me, I wanted to share my screen here, full screen with this image. In conclusion for today's webinar, I'd like to mention that the journal here, The Frontiers of Computer Science, is planning and producing to publish a special edition of their journal on neuromorphic embodied intelligence. The special issue aims to bring together the latest advances and emerging trends in this rapidly developing field. And researchers working in related areas are invited to contribute their latest research to that special edition, including Dr. Cowenberg and Dr. Bian. Thank you to all the participants for joining today's webinar, our speakers, Professor Gert Cowenbergs and Professor Shizhen Bian. Thank you also to the Frontiers of Computer Science, to iGroup for putting on this event together with us here at Newswise. We hope today's discussion has provided new insights into the future of neuromorphic intelligence and that you found this useful. Thank you very much, everyone. That will bring today's presentation to a close. Have a great rest of your day. Thanks very much.
Thank you.
Thank you.